Okay, ladies and gentlemen, I present to you a man who may not need much of an introduction, but I'll give a short one anyway. Clinton Roy. Clinton is an open source engineer who does a lot of low-level networking and operating systems level work. You may have seen him around. Please give it up.
Good morning, everyone. Before I start, I have to say that this talk that I've put in was an attempt to get the author of the library that I'm talking about to put in a much better talk proposal. That attempt failed. He called my bluff, but all of the work and most of the slides are actually due to Russell up the front. So a round of applause for Russell as well, please. All right, so we're talking about parsing things. A lot of people are comfortable parsing things with regular expressions. This talk is about what to do when regular expressions aren't enough. Ooh. Okay. So if you hunt around on the web, you'll find a lot of people have asked many, many times how to parse things like XML and HTML with regular expressions. There's a fairly famous quote, and it ends like this. In short, you can, but you really, really, really shouldn't. It's the wrong tool for the problem. So, a lot of the nice things with parsing is that it is, to a large extent, an academically solved problem. The problem with that is that you get a lot of strange words when you're describing the problem. So HTML is a Chomsky type 2 grammar, otherwise known as context-free, and regex is a Chomsky type 3 grammar, which is regular. And these are two different classes of languages. So a tool that can parse one won't necessarily be able to parse the other. So there is an answer to parsing most of HTML/XML with regular expressions, and it's down here at the bottom. And, oops. It's down there at the bottom, and it's quite a while. And this parses most of HTML, not all of it, but a fair chunk of it. So if you just copy and paste that into your web app, you'll be good to go. So the takeaway point there is if you're doing that in regular expressions, it's the wrong tool for the problem. So if you want to break it down into the things that the classes of languages that regular expressions can't parse, it's structure, it's counting. So, for example, with a simple nested list here of HTML, you can get kind of close with parsing bits and pieces of it, but the things that you can't do is you can't check that you've opened and closed your list properly. Regular expressions just can't do that. They can match the opening, they can match the closing, but they can't match the closing and the opening up. So the typical example you use when parsing something is a mathematical expression. And the reason we do that is it is a free-form text string, but we have a lot of history in maths of using particular conventions. And so the job of the parser is to take what is essentially a free-form string and apply the conventions that we would normally apply to it and make that a computer program. So what we see there as a set of strings is actually a set of operations applied in a certain order. And that's the job of the parser is to break that string up into a data structure that represents the order of those instructions. So that large expression, we can break that down into a smaller expression. So on the left, a for and a plus, and a larger expression. So at the top of our data structure that explains that, we might have that tree there. So you've got the root of the tree being the plus, and the left being the number 4, which is an expression, and the right being all of that. And then we take this large expression on the right, and we reparse that, and we break it down until we've broken down all of the components. So if we keep doing that, we turn that string into this data structure. So this is a tree represented as a Python tuple. So we've broken it down into an expression of the entire tree with the number, the plus, and then the expression on the right, and the power operator, and the plus positive operator on the right there. And the important point here is that we have broken this input down into a data structure that follows the conventions that we follow in maths. It's relatively easy to break that string down into a data structure that doesn't follow the conventions of maths, and that's what this talk is going to try to explain. How not to do that. So, regular expressions are still used in parsers. You can very much think, in most parsers, you can think of the regular expressions as being your basic level, and then on top of that, the parser. So inside a parsing engine, we use the regular expression to break up the input into a bunch of tokens, so the smallest bits of your language. So there's some terms here. So tokenizer and lexer, pretty much the same thing. You feed in the input and it breaks it up into the smallest tokens. The grammar is a bunch of rules that describe how to take those tokens and join them up into a data structure that describes your language. Your parser generator takes your description of your language and generates the computer program, the parser, that will actually do the work that you want it to do. So, inside your grammar is a list of rules. So, one of the rules that we can see here is that an expression is an expression with a divide by token and another expression. And in our grammar, we'll have a whole bunch of rules, and this one is one of those rules, and that's a pattern. So a grammar is just a collection of those sort of productions. And you can see the recursive nature of the parser. We're not, in each production, we're not trying to solve the entire parsing problem, we're only trying to solve one part of the parsing problem. So here we've got addition, power, positive numbers, negative numbers, bracketing, and then down to numbers. And the job of the parser is to see those little bits and put them all together into a data structure that describes your entire input. Now, there are a lot of tools out there that will take your language rules and generate a parser for you. You might have heard of the standard Unix ones, Yak and Bison, and they will generate C and C++ parsers for you. There are a lot of libraries out there that will generate Python code for you, but they're all awful. Russell has written one which is wonderful. I'm his #1 fan of this library. You write it in Python, it generates Python. You write it in Python syntax as well. So this here is a it would be the starting point for writing a grammar that parses our mathematical expressions. So we import a few special things. We define our language expression around as a subclass of a generic grammar class. And as class level attributes, we're defining an expression to be all of those rules that we previously looked at. This is a special token that just means this point in the data structure. And we also have the tokenizer rule there. So the RE is regular expression. So when we're trying to match a number, we are matching 0 to 9 plus. And everywhere in here where we see a literal string, that is also a token. Now, this is the beginning of a language that will parse it. If you throw a lot of mathematical expressions at this parser, some it will parse, some it won't parse, and it definitely won't follow the conventions that we would normally apply. So things like multiplication coming first and addition going last. Now, what we're basically saying here is that this grammar is ambiguous, and that's a particular bit of terminology that we're using. And it means that to take this grammar and produce a computer program that will only generate one data structure, we need to give it some more rules. Well, we need to give it some more hints about how to apply these rules. So, when all of your literal strings and all of your tokens, internally, they get put together in one big regular expression. So there are some special cases for dealing with this. So on this previous example, it will take all of these literal strings and these tokens and put them in one regular expression and just go this A or B or C or D. And that's the first step that we use to break up your input string down into the tokens. So you can use regular expressions. You've got the idea of keywords, which are literals, but it also means that if you're writing a language that's got variables and you declare a token to be a keyword, you won't be allowed to use a variable called and, for example. And the grammar will not allow you to do that if you want that to be the case. And if your parser is given a program and it can't understand something, it will raise the unrecognized token. Right, so when we said that this was the start of the production of a parser, the parser generator, Lrparsing, will look at our rules and it will try to generate a program, and it will discover that it's really easy to give it a string and to be able to generate two different data structures for that same string. So it's an ambiguous grammar, and it won't let you generate a parser for that. So it will give you an error message attempting to explain what the issue with your grammar is. So we've given it these two rules here, and the caret is indicating that that's where the ambiguity is. So if we see a literal plus, we could be in one of two rules, and we really only want to be in a state where if we see a particular token, we're only in one rule. And it's being as helpful as it can be to describe the problem with the grammar here. So, this gets into a little bit of the internals of writing a grammar, but you can map these rules back to the rules that you've added, and the idea here is that if you've given it this input, it could generate a parse tree here, or it could generate a parse tree there. And the grammar doesn't like to guess, it wants to know. So you need to give it an extra hint. And the extra hint here is in this priority list. So this means that instead of a set of rules that can be applied, it's a list of rules with a priority. So if you can apply the brackets rule, match that one, and then the number rule, and then the power rule, and then the plus and the minus rule. So that will remove one sort of ambiguity in our grammar. Unfortunately, we fixed that sort of ambiguity, but the thing to notice there is that priority is a feature of Lrparsing that makes it easy for you to add priority to your rules. Instead of having to do all sorts of horrible things with your grammar, you just say, these list of rules, run them in this priority. So it's a very nice feature of Lrparsing. Unfortunately, once you fixed those grammar problems, we come up with some more grammar problems. Now, the problem here is that it tells you exactly which rules it's seeing the problem in. It's going to get a token and it's not going to know which rule to go with. The problem is that the rules that it's talking about are internally generated ones. They're not ones that we've written. So we have to go in and ask for a little bit of debugging information. So this is the language that we've got with the priority, and this one still has a language ambiguity. So we run it, we try to compile our grammar, and we catch the problem, and then we will show the internal productions, and that will make it a little bit easier to work out where the issues are. And you can see here that the expressions and the priority, so those are the ones that we've input, and then internally Lrparsing has generated these internal states, and those are the states, those are the production rules that it's having problems with. So when you have a look at that, the problem here is when it gets into this state and it sees a slash, it's not sure which rule to use when it sees the slash. So if you substitute in that token into your rules, you'll see that you've got two patterns that try to match. And again, it means that we could match that, or we could match that or that. And it won't let you compile a grammar with that ambiguity, so we have to give it some more hints. So this is basically, do we mean A plus B brackets plus C, or A plus brackets B plus C? And it's just deciphering between those two. So the hints that we've added here are the shift operators, and they define your associativity. So in the maths operations, we're just defining the associativity. So in the plus example here, it just pushes the associativity left. So if you've got A plus B plus C, it'll just put the brackets on the left. If you've got the power operator, so you've got A, power B, power C, it will use the rules from the right. So it'll put the brackets on the right and go back left. Now, some of these things are specific to mathematics notation. You won't always get these problems in a regular programming language, but you do get things in regular problems where you're trying to parse things and things become ambiguous. And when you're explaining these hints, it's often the only common denominator that people understand is a mathematical language, but all of these tools do get used outside of the mathematical grammars. So after we've fixed those two ambiguities, we now have a final parse tree. So this is a tree. It's represented as a nested list of tuples. Now I've done some work to turn this into a Python AST tree. That might even be ready to actually give a proper talk about next year, maybe. But we are able now, the thing here is now that we've got that grammar, any input string that only has the tokens that we've allowed, we can parse that and it will only generate one parse tree. And we are guaranteed that for all inputs. That's the really important thing. Once we've got a grammar parsing Lrparsing's ambiguity checks, it will work for every single input. So, Lrparsing comes with a number of optional extras that make typical things easier to do in parsing than you otherwise would. So, if you were writing something that took a list of arguments, so like a Python function, taking an arbitrary list of things, you can say, instead of defining a pattern to match an object followed by a comma, followed by another object, and possibly having a final comma or not, you can just use a list. So we'll take a list of, say, expressions. We'll delimit them by commas. You can have an empty list or not. You can have a maximum number of those lists and the optional trailing comma. It's not hard to write by hand in Lrparsing, but it's a common enough thing that Russell's just put in a bit of syntactic sugar for you. It's common when writing your rules to want to write your rules, your patterns in such a way in your code that you write the outermost rules, so the rule that describes your entire input language up the top, and then break it down below. The problem with that is that you often hit an issue where you want to use something before you've defined it. So here, I'm not actually sure that one's right, is it? With the reference?
Yeah, it defines expr last.
Okay, but it's defined it there as well.
Let's say.
Oh, right, yes, right. Yeah, here we're defining, we're saying that we are going to define the rule expression further on, but for now, we're just letting you know that it's there. So in this call, we can use expression, and then later on, we can actually define expression. So that just lets you reorganize the patterns in the Python program in a way that makes sense when you're defining the language. Doesn't change the grammar at all. You could move that expression up above there and not have that reference, but it often makes more sense to go from the big objects at the top of your grammar and the smaller objects at the bottom. And similarly, another bit of syntax for repeating symbols. And there's a couple of rules for that. So you can have optional symbols. So you can have this expression or not have this expression. You can have some of these, many of these, and it's a naming convention for this. So if you want to say that you can have this keyword multiple times, you can say keyword times n, or you can say many. You can use the Python syntactic sugar, or you can use a function. So if you want to say A or B or C, you can do that like that, or use that syntax. And similarly for this. And there's a simple way for defining tokens as well, where you just pass in a string and it will break it up on the white space. Doesn't change the language, it's just being It's just a syntactic sugar for doing things slightly easier. So this is where we start to get into the guts of the parse tree and showing you parts of the token. I'm running a little short on time, so I'll skip past some of that. Right, yes. So because it's a Python parser, it makes it easy to parse out comments and whitespace, so you can relatively easily parse Python with it. But it means that if you're writing a programming language or you're writing a configuration file format for configuration files and you want to add comments, Lrparsing makes it really easy to add comments to it and strip them out, and so you don't have to worry about it in the rest of your grammar rules. So if you wanted to run your calculator, you can add options to you can add code to the nodes in your tree. So for example, when you've parsed the binary, you can run the code associated within its tree, and if the operator is a plus, you can use operator add and divide. So you only want to use this on small examples like the calculator, but essentially it's a quick and hacky way of turning your parser into, or turning your calculator into an actual program. Error messages are reasonable. They're not great, but they're pretty good. So here, 2 plus 3 divided by minus 1 to match binary expression state. So that's the sort of class of error message that you'll get, and you get all the information about exactly where in the string that is. So you can put up a string saying a caret, saying I was expecting this in this value. It is quite quick to make a parser. So for the stuff that I do, I make the parser on the fly. If you've got a large language and you want to pre-compile it, Lrparsing supports that. So it will generate compiled Python code, and then you can import that later at runtime. Lrparsing is very quick, as well as being elegant, well documented, and it is also very quick. So here's some quick comparisons with other parsing suites for defining a particular grammar. And Lrparsing is the shortest. Everything else is much, much slower. Lrparsing comes with a tokenizer built in. All these other ones, you've got to do the tokenization yourself as a separate step, and we have copious amounts of documentation. So that's the information for the talk, and hopefully I'll be able to pull up the documentation. And what Russell has basically done here is written a book about parsing, and as footnotes on each page, it's here's how you do this standard parsing task in Lrparsing. So this is the very extensive documentation for Lrparsing. It is basically a little mini book on parsing. And there are some really good examples that come with Lrparsing. He's got an example of where he's parsing SQL, and he's using the SQLite test suite to, so all of the SQLite test suite, he runs that through his parser. And what's the one that you... He's also got, in one of his examples, parsing Lua and translating that to Python. So that's a fairly extensive example that he's got. Which works, yes. No, it works. Lua is a much simpler language than Python, so it's much easier to go from one way to the other. If it was going from Python to Lua, that'd be a little bit more fun. So in short, Lrparsing is a wonderful Python project for doing parsing. So if you're bumping up against something and you're trying to parse it with regular expressions and it's too hard, have a look at Lrparsing. It's the Pythonic solution for parsing. It's fast, it's easy, it's very well documented. Thank you very much.
Thank you, Clinton and Russell. Did anyone have any questions? Yeah, come on up. Come on down.
Russell, you should probably answer questions.
Thanks for the great talk. I've looked at Apply a while ago and wasn't quite happy about it for various reasons. What's your take on Lrparsing in terms of how do I actually add productions to my parsing tree? So I have my parsing tree and I have certain productions for different words, and I will actually want to go and apply this parsing tree to apply the productions based on my parsing tree.
So if I understand the question correctly, what you're asking is I've got my parsing tree and now I want to use it to generate some code or do something like that. Yeah, you saw a simple example with the arithmetic one, but it only works for simple. There is another example which I use with Lua, which you set up a parallel tree. You define these same symbol names in the tree, and what happens then is in that class they get called. So as soon as the parser recognises a unary expr, it calls your function, passing it whatever you've generated so far, and then you turn it into code. There's a bit of boilerplate you've got to do to get going, but once you've done that, this is the technique I use for Lua.
So the aspect of Lrparsing that I would like to improve is to generate ASTs, and I've got some code that generates ASTs using the Python AST classes, and then you can use the same AST walk functions that the Python AST uses. I don't have a nice generic solution for that. I've got AST generation for specific classes and types of languages, but not for everything at this point in time.
Thank you.
Hi, thanks for the talk. I just have one probably annoying question, but I see a lot of print statements without brackets. Does it support Python 3?
Same code works both Python 2, Python 3. The examples you saw there were because the slides were done in Python 2, but it's completely compatible with both.
There is full code coverage for all of the code.
In both Python 2 and 3.
In both Python 2 and 3, you run the test suite, all the code is tested.
Okay, so no further questions? All right, well, let's show our rowdy side once more for Clinton and Russell.